Hello, calculus fans, and welcome to section 6.5, where we talk about the average value of a function. This topic is a little simpler than what we've been working with in chapter 6. So the calculus is a little bit less intense for this. So we start off just with the idea that if you're looking for the average, and we're speaking of the mean in this type, of a finite set of data, it's pretty easy. We just add up all the numbers and divide by how many numbers there are. So if you have a finite set of data like this, these are snowfall readings from the National Weather Service, and these were taken at Ford International Airport. And we had this snowfall for a handful of years here. And so if you wanted to find the average, it's pretty simple. We just add up all the inches. And since there are 10 different years here, we divide by 10. So we would end up with 234, which is the total inches. If I add up all of these numbers here. And then there were 10 years, so divide by 10. And we get 23.4 inches for an average. And again, in this case, the average we're talking about is the mean. So as you know, there's other types of averages. There's the mean, the median, the mode, the trimmed mean, and all different kinds of averages. But we're talking about the mean here. Okay, pretty simple. To find the average value of a finite set of numbers requires only arithmetic. But how do we find the average value of a continuously varying function? So here we've got this function, and you can see it varies, right? And not only does it vary, but how many points are here? Like here there were 10 different years, right? 10 different years here. Well, how many different inputs are there here along this x-axis? Right? There's an infinite number of them. So we're dealing with something a little bit different in this case. So what we'll do is kind of what we always do in calculus. We're going to break up this area here into a bunch of pieces using rectangles. So I've got some lines here that we're going to use for rectangles. And then just like always, what we do is we find some point in here to use to get the height of the rectangle. So sometimes it's a left end point, sometimes a right end point, sometimes a midpoint, or just generally it could be any point. So let's just say we pick some points in here. So let's go with, we'll just say we're going to pick this point here. I'm just going to call this x sub 1 star. This would be x sub 2 star, just meaning it's any point in there. Midpoint, left end point, right end point, it really doesn't matter. And so this one will be x sub n star. And then I'm going to use these points to find the height, right? So we'll use these points. I guess it looks like kind of the midpoint in this case. But we use these points to find the heights that we're going to use for our rectangles. So a lot of this is going to look familiar. It's the same sort of thing we do all the time in calculus. So we're going to break this interval AB. So this interval AB, we're going to break it up into n subintervals. So then each subinterval would have this length delta x. And of course, delta x is just going to be these, like the base, right? The base of our rectangle, so that would be length delta x. And that's just going to be b minus a over n, right? Because b minus a would be the distance from here to here, right? Just b, take away a, whatever you're left with, that's that distance. And you divide it up into n pieces. And then, so if we had n rectangles, each of these bases of our rectangles would be this length, which we're calling delta x, right? Delta x, delta x, delta x. And then we're going to choose these sample points, these x sub I stars in each subinterval. And we use those so we can find the heights. Okay, so then if we're going to find the average of each of these heights, this would be the height, right? So f of x sub 1 star is the height there, right? The function at that point. So we want to find the average of all of these. Well, if we have a finite number of rectangles, it's not too bad. We just add these up. You take that function value, this function value. We add all of these up. So this would be f of x sub n star We add all those up and we divide by how many there are, which would be n. That would give us the average of a finite number of them. Okay, then also if you notice that since delta x is b minus a over n, then if I took this equation and multiplied both sides by n, what I would get is b minus a equals n times delta x, right? And then that, remember this symbol means implies. So if this is true, that implies this is true, and that implies. So here what I'm going to do is just solve for n. So I'm going to divide each side by delta x, and we would get n is equal to b minus a over delta x. So what we're headed for here, we're going to come up with a formula that will allow us to find the average value of a continuous function on some closed interval. So that's what we're headed for right now. So then once we have this, once n is equal to b minus a over delta x, I'm going to substitute this in for this n right here. So that gives us this. All right, I took this and plugged it here to get this. So I get this equation, or this expression here. And now what I want to do is I'm going to multiply the top and the bottom of this fraction by delta x. So think of this, I'm going to multiply by delta x over delta x. And of course in the denominator, it just means that when I multiply this by delta x's will cancel. So I'll just have b minus a in the denominator. In the numerator, when I multiply by delta x, I just have delta x times the numerator. So that will give us this here, right? So we're multiplying this by delta x and then the bottom also by delta x, so we get here. And then what I want to do is I want to factor this, or pull this b minus a out in front. Pull it out in front here. Okay, so if we do that, then we'll get 1 over b minus a times delta x times all of this stuff. Same as what we had before. Okay, this is okay, right? Because think of like if I have 1 over b minus a times all this, if I were to multiply this straight across, you get 1 times this, because this would be like a fraction over 1, and then b minus a times 1 would get us back here. All right, so far we're making some progress, but we want to write this a little simpler way, because this really, if I have 1 divided by b minus a times all of this, I could really distribute this through, right? So a simpler way of writing that is to use sigma, summation notation. So I'm just going to do one more thing here. I'm going to rewrite this as the summation as I goes from 1 to n of f of x sub I star times delta x. Then you can see that this right here is just replacing this, just a little more concisely written, right? Because you can see, since this is summation, you start with 1, you plug a 1 in here, multiply by delta x, and then you add, because it's summation, then you plug in a 2 and a 3, and you go all the way to n, so that this is equivalent. Okay, so now we've got Riemann sum here. And as you know, in calculus, when we get a Riemann sum, we have been known to take the limit of the Riemann sum. So we're going to let n approach infinity, so this n's going to approach infinity. So we're going to take the limit of this whole thing as n approaches infinity. Then since these are just constants, we can bring this out in front of the limit symbol. So we have 1 over b minus a times this limit. The limit of this basically Riemann sum here, right? So these are all of the heights of each rectangle times the delta x. And then we know that this is just equal to the integral, right? This is equal to the integral from a to b of f of x dx. And this is basically the formula we're going to use. So if we want to find the average value of a continuous function on some closed interval ab, it's right here. And there's not really much to it. It's just the average is 1 over b minus a times the integral of f of x dx from a to b. So there's not really too much to it. We just have to know that formula, and then we can figure out these average values. So they're asking us for the average value of this function, sine of x on this interval. So just to get an idea of what they're asking us, I'm just gonna draw a quick picture here. So sine, we know what sine does, right? Between 0 and pi, sine just goes up and back down. So sine just goes something like this. That's the sine curve. And we're looking for the average value here. So like we know at pi over 2, the value of sine is 1. We're not 0 and pi, the value of sine is 0. So we're sort of like saying, what if we could take the average of all of these heights, right, of all these y values here from 0 to pi? Like if we could somehow take every single one of these heights, each one of these y values, and take the average of all of them, what would it be? Well, it seems impossible, right? There's an infinite number of values between 0 and pi, so we're looking for an average of an infinite number of heights of this, right? Think of the height of this function, or the y coordinate, right, to give you this gap here, this height. So there's an infinite number of them. So we'd have to add up an infinite number of numbers and then divide by infinity and somehow get a number. Well, we can do it because we're going to essentially be using the limits, right? By using the integration. So let's just try it. Let's see what the formula will give us. So the average value is going to be 1 over b minus a. Well, here's b, here's a. So b minus a is just going to be pi minus 0, which is pi. Then we integrate from a to b, which is 0 to pi, sine of x dx. Okay, so in Calc 1, you learned the antiderivative of sine is negative cosine. So we will get 1 over pi times negative cosine of x from 0 to pi. Okay, so we need some cosine values. So whereas this is the sine curve, let's just quickly sketch the cosine curve here. Here's pi, here's 2 pi, and of course the cosine curve, cosine of 0 is 1, so it just goes down like this. So with that in mind, when we plug in the endpoints, we will get, I'm just going to bring the negative out front here and just go 1. I'm going to do it like this. Let me just rewrite this, pi to 0. Okay, so then when we plug these in, we get negative 1 over pi times cosine of pi minus cosine of 0. And we can see right here the cosine of pi is negative 1, cosine of 0 is 1. So this is going to give us negative 1 over pi minus 1, which gives us negative 2, or 2 over pi. So the average value is 2 over pi. Now that's approximately equal to 0.637. So the average height here, if we drew a whole bunch of vertical lines here, and we took the average of all of these lines, all the infinite number of them, the mean height is about 0.637. All right, so to find the average value, there's really not a whole lot to it. We developed this formula. Now we can just use this formula. So they ask us another question about the average value of sine of x, but now they give us a different integral, or a different interval, sorry. So now they're saying between 0 and 2 pi. Now this one, we can probably figure it out just by looking at the graph. So let's just consider the graph of this one. So we've got pi and 2 pi. We know the sine is going to go something like this. So if we want to find the average value of sine of x between 0 and 2 pi, Well, here's a whole bunch of positive y values, right? Here's a whole bunch of the same values that are negative. So what do you think the average would be here? Well, if you keep in mind that these are positives and these are negatives, it looks like the average value is going to be 0, right? They'll cancel each other out. So let's just see. Let's see what happens here. So the F average is going to be 1 over 2 pi, right? Because it's 1 over b minus a. Here's b, here's a. And then we integrate from 0 to 2 pi, sine of x dx. Once again, we know that is going to be 1 over pi times negative cosine of x from 0 to 2 pi. And I'll once again just pull out the negative, make it easier to deal with. Cosine of x, okay, from 0 to 2 pi. So this will give us cosine of 2 pi minus cosine of 0. Okay. And now looking up here at the cosine graph, this cosine graph, cosine of 2 pi is 1 minus cosine of 0, which is 1. So you get 1 minus 1, which gives us 0. So it's what we expected. The average value is 0 because all these positive values cancel out all the negative values. In this section, we look at something called the mean value theorem for integrals. Okay, but before we do that, let's quick review something you probably saw in Calc 1. And it was also called the mean value theorem, but this time it was for derivatives. So what it says is if f of x is continuous, as you know, in calculus we study continuous functions, or at least we study functions where they are continuous for the most part. So if f of x is continuous on this closed interval a, b, and differentiable on the open interval a, b, then there exists a number c in a, b such that f prime of c equals f of b minus f of a all over b minus a. And you may recall, this looks kind of like a slope formula, right? Because it is. This is the instantaneous rate of change, right? The derivative of the instantaneous rate of change at c. And this is the average rate of change. So let's point this out. This is the average rate of change. Average rate of change. This is the instantaneous rate of change. So geometrically it just says this. We've got this function here, y equals f of x. And if we consider this point, let's say f of a, to the y coordinate there, and f of b. So this point is a, f of a, and this point over here is b, f of b. And now let's consider the line through these 2 points. So if we have this line that goes through these 2 points, something like this. Well, if we want to find the slope of this line, we could use the slope formula, right? y2 minus y1 over x2 minus x1, so the slope through here. So the mean value theorem says that there exists some number c in this open interval AB, so there's some number c in here such that the instantaneous rate of change, the derivative, or geometrically the slope of the curve along, slope of the tangent to the curve along here is equal to this slope. So there's some point C somewhere, and I'm just gonna kind of wing it. Maybe it's like right here. Maybe the tangent there. My drawing's not perfect, but Let's see if this comes straight down here. So this is point C. So the mean value theorem says that there is going to be some C here where if I come up and take the tangent to the curve here, that slope equals the same as the average slope. And there's some applications in Calc 1 that when you study this you may look at, but most of the value of the mean value theorem will be studied by you if you're so lucky that you get to take, I guess it's called, there's a couple names. It's either real analysis or advanced calculus. It's usually the class you would take if you take Calc 1, Calc 2, Calc 3, then you take maybe differential equations, and then a lot of times the next class with calculus would be real analysis, just for math majors mostly. But then you'll see that the mean value theorem here from Calc 1 and also the mean value theorem we're going to look at here, they're used a lot in the theory of calculus. There's not as many applications, although there are some. But as a Calc 1 student, you'd maybe look at an application and then you'd be tasked with finding this point C. As a Calc 2 student, we're going to look at the mean value theorem for integrals, and we'll do a couple things with it. But its real importance will be discussed further down the road in real analysis or advanced calculus. Okay, so let's look at this new one though, the mean value theorem for integrals. Starts off in a similar fashion. If f of x is continuous on AB, then there exists a number c in AB such that f of c equals the average value of this function. So let's look at this and kind of see what this is saying. Okay, so we've got this statement here. And what this is saying is the average value of the function. The average value of the function is the same as the function at point C. And the mean value theorem for integrals just says that there exists this point C, that it exists. This point C exists such that the value of the function here is the same as the average value of the function. And then it's easier to see what this is saying if you think of the geometric interpretation. So to do that, just ignore this part here, just ignore that, and just say we've got f of c equals this. Well, if we wanted to, I could multiply both sides by b minus a to get rid of this. So I'd have this left, so I'd have this equals this times b minus a. So you'd have b minus a times f of c. And then when we look at a picture on the next page here, just remember this is going to be the base. This is going to be the height. Okay, so this is easier to see maybe than this because we're going to see it in the picture. So we've got base times the height. So let's take a look and see what it is saying. So if you recall, the definite integral can be interpreted as the area under the curve y equals f of x. All right, so this definite integral we can interpret as the area under this curve from a to b. And then the mean value theorem for integrals says that for positive functions, so these are functions that are above the x-axis, there's a number c in this interval such that the area of a rectangle with height f of c and base b minus a equals the area under the curve y equals f of x from a to b. So what it's saying is that if we think of the area under this curve from a to b, all right, so let's get a picture of that. So you got the area under the curve from a to b. So this area here whatever that area is, we're going to be able to find a c such that we can create a triangle in here, or sorry, a rectangle in here that has the same area. Okay, so let's see if we can find something that looks reasonable. Let's say we've got this point C here. And come up here, and then we make a rectangle here. So the theorem says that there's some C here where if I now find the area of this rectangle, this area of the rectangle is the same as the area under the curve. So if you look at what we've got here, this is f of c, right? That's the height. Then the base of the triangle is going to be b minus a. So this is b minus a. And the mean value theorem just says that we'll always be able to find this c, this point C, that allows us to make this rectangle that has the same area as the area under the curve. Okay, so as a Calc 2 student, a lot of times when you study the mean value theorem, you're just going to be going to be asked to find this c. Okay, so as an example of that, we've got example 2 here, which gives us this function. So you got 4x squared, or 4x minus x squared in this interval 0 to 3. So this is the kind of question they'll ask us in a Calc 2 class. So first they'll say, find the average value of this function on this interval. Okay, so we've got a formula now we can use. We developed earlier, so we know that this is equal to 1 over b minus a times the integral f of x dx from a to b. So if we do this, well, b minus a is going to be 3 minus 0, right? Because this is a and b. So you're going to get 1/3. Then this integral from 0 to 3, 4x minus x squared dx. Okay, so this is a pretty straightforward integral. We can use the power rule a couple of times. So we'll get 1/3 times, let's see, 2x squared minus 1/3 x cubed. And we evaluate that between 0 and 3. So we get 1/3. So I plug in the 3 and I will get 2 times 9 minus 1/3 times 27. And then plugging in the 0 is not going to add anything, so it would be just basically minus 0. I guess I'll just throw that in there. So that will give us 1/3 times 18. 1/3 of 27 is 9, so we get 1/3 times 9, which gives us 3. So the average value of that function on the interval from 0 to 3 is 3. And then the geometric interpretation, well, if we were to graph that function, okay, it looks something like this. We'll make a quick picture of it. You can put it in your graphing calculator, but it looks something like this. It goes, let's see, 1, 2, 3, 4, 1, 2, 3, and it does something like this. Let's see, it goes here. Just sort of sketching it in here by hand, so of course it won't be perfect, but something like this. So the geometric interpretation is basically find the average of all of these heights, here. So wanted to find the height of the function there, and there, and there, and there, and there, and there, right? The infinite number of vertical lines here, and we're looking for the y-coordinates to find the heights here. Because that gives the value of the function between 0 and 3. And we know it's going to be 3 because we just found it was 3. So the average of all of these red vertical lines, all the infinitely many of them, the average height of the red line is 3. Okay? This seems actually surprising we could even do that because there's an infinite number of them, but we can using calculus and using the ideas of limits. And then what they're going to do, they want us to find the c such that the average value here, which is 3, equals f of c. Okay, so to find f of c, we can just go back to the original, right? So f of x was equal to, what was that one? It was 4x minus x squared. So the average value was 3, and we want to set this equal to f of c. Well, f of c is just going to be 4c minus c squared. Right, here's f of x. So I'm just going to plug a c in here and then solve this for c. So to solve this for c, I am going to just bring everything over here so I can have a positive c squared. So I'm going to add c squared to both sides, subtract 4c. So I would get c squared minus 4c plus 3 equals 0. Second degree equation, we can solve all second degree equations, right? Because we have the quadratic formula. But if we can factor, it'll be even easier to solve. So let's try factoring. Remember, second degree equation, quadratic formula works 100% of the time. Even if there's no solution, you'll find there's no solution because you get a negative under the radical. Factoring doesn't always work, but when it does work, a lot of times it's it's faster. We just have to see if this is factorable, which it is in this case. So this one does factor. So you have c times c, 1 times 3, and then we've got a minus and a minus. So if this times this is 0, could mean, it means that either this is 0 or that is 0. c minus 1 equals 0 or c minus 3 equals 0. That means c equals 1 or c equals 3. So the mean value theorem says there's going to be at least one value of c. We have 2 of them. And we just have to check and make sure that these are in the interval, and they are. So both are in the interval 0 to 3. So they're both in there, so there's 2 c's. And then part c, we want to take a look at the geometry and see what it looks like. So we want to sketch a graph of the function. So once again, I'll just draw a picture here. So I'm just going to go 1, 2, 3, 4. 1, 2, 3. So our function looks something like this. It comes up, goes like that, between 0 and 3. Okay, so now it says sketch a graph of f, so here's f, and a rectangle whose area is the same as the area under the graph of f. So the area under this curve here between 0 and 3, well, to sketch the rectangle, we can use these. These are the things that if we use these for the height, the function evaluated at these spots for the height, we'll get a rectangle. So at 1, if I go up to 1, it's here. Actually, I want to do that one in red. And 3 also is here. So when you plug 1 or 3 into the original function, it turns out to be 3, which means that if we did this, the area there in the red under the rectangle, you can see my picture is not perfect. This actually looks like it goes up a little higher in reality. But the area in the red in the rectangle is the same as the area under the original curve. Okay, so that's pretty much it. 6.5 is a less intense section than what we've been working with, so it'll be probably a little bit of a breather. You can catch up a little, but still give it a try. And of course, as always, let me know if you have any questions.